All right, hello everybody. Welcome back. We are looking at the second video. This is again part of chapter 20 in the statistics modeling our world curriculum. It is focusing on hypothesis tests for proportions. Right? We are specifically saying just for proportions in this video. In the last video, we introduced what a hypothesis was, the reasoning of a hypothesis test, and that the ultimate goal is to calculate a p-value. A p-value being the probability that our observed event would have happened given that the null hypothesis is true. In this video, we will be going and talking about the 4 basic steps to conducting a hypothesis test, and talking about each of them in detail and doing an example problem along the way. Okay, so let's go ahead and get started. The 4 basic steps to a hypothesis test are: first of all, we need to create a hypothesis. What is our null hypothesis and what is our alternative hypothesis? Once we have done that, we need to check our assumptions and conditions. Are our conditions met so that we can conduct this test to test the hypothesis? Then we need to do the mechanics of it. We need to actually, in the mechanics, we can sort of say this is where we find the p-value. And there is a test statistic that we calculate to make that happen. And then finally, the last thing is we need to write our conclusion. And a kind of way to remember that would be hammock, a nice little hammock, right? So that's how I will refer to it from now on, is our hammock, our hypothesis, assumptions, mechanics, and conclusion. And then just as a side note, on the AP test itself, they do expect all 4 of these steps when you're conducting a test. It is almost like a guaranteed fact that there will be a hypothesis test of some type on the free response section. And typically the way that that's graded is you get 1 point each on these. 1 point each. So you get a point for stating the correct hypothesis. You get a point for correctly doing your assumptions and conditions. You get a point for finding the appropriate p-value, and you get a point for finding the conclusion. And as another side note, it's most of these tests, the average score on them tends to be a 1 or a 2. So these types of things, as long as you identify the correct test, this should be like, this should be givens, right? These hypothesis tests should be like the easy one on the AP test, because there's a lot of thought that we have to place into it, but they're in a lot of ways very formulaic, and we kind of do them. The process we follow pretty exactly. Okay, so let's jump in. Let's do some of these parts in detail. The first one is the hypotheses. So we need 2 hypotheses when we do something. The null hypothesis. So to perform a hypothesis test, we first translate our question of interest into a statement about the model parameters. What that means is I need to read my question stem and come up with what I am trying to prove. What am I trying to show? So the null hypothesis is typically whatever our parameter is, may it be like a proportion or a mean, and we use the equal sign with a null hypothesis, and then we talk about whatever that hypothesized value is. What is the value that we are claiming it to be? What are we going to assume this value is before we test it? The alternative hypothesis, the H sub A, contains the values of the parameter we consider plausible when we reject the null. In other words, it's kind of what we're looking to, it's kind of what we're looking to prove in many ways, okay? And the alternative hypothesis typically is parameter, and then we will use either the less than symbol, the greater than symbol, or a does not equal to symbol, and then it's the same hypothesized value. So I gotta look up there. Hypothesize. There we go. Hey, look at that. I can spell. Hypothesized value. So the parameter here and the hypothesized value, we generally put the same. The only difference between the alternative hypothesis is that are we claiming that it's actually much smaller than the hypothesized value, in which case we would use this? Are we claiming that it's bigger than that, or are we claiming that it just doesn't equal that? Okay. So let's look at an example. A large city's Department of Motor Vehicles claimed that 80% of candidates passed driving tests. But a newspaper reporter's survey of 90 randomly selected local teens who had taken the test found that only 61 passed, which is an amount smaller than 80%. So the big question of this is, does this finding suggest that the passing rate for teenagers is lower than the DMV reported? And so we're going to first start by writing the appropriate hypotheses. I don't think I wrote them down. So we have a null hypothesis. And remember, the null hypothesis is sort of like the claimed amount. So we have our parameter, P, equals, and then what are we saying is the claimed amount? 0.80. So my null hypothesis is that the proportion of teens who take the test is 80%. Okay, but now this reporter says that only 61 of the 90 passed, and that's smaller than 80%. So then we're going to say we're making the claim here that the parameter, the proportion, is actually smaller than 0.8. So remember, we're making the assumption that the DMV is telling us the truth, that it's 80%. However, we are going to try and disprove that by providing evidence that the alternative hypothesis is more likely to be true. Okay, so there's my hypothesis. H sub 0, my null hypothesis, equals P equals 0.8. Well, my alternative hypothesis is that my proportion is actually less than 0.8. And I'm using less than instead of greater than because we're talking about only 61 out of 90 passing, which is a smaller number. So there's my hypotheses. Let's talk about assumptions and stating a model. So anytime we do a hypothesis test, we need to specify the model that we're going to use. Whether it's a Z model or things we're going to talk about in the future like a T model. And we're going to use that model to test the null hypothesis and the parameter of interest. Oh, these are our assumptions, by the way. That came up in a weird order. All of these models require assumptions. And so these assumptions we use to talk about certain conditions that have to be met in order to run the test. When we do this step, we need to check those conditions, and then we need to write a statement that says something like this, right? Because the conditions are satisfied, I can model the sampling distribution of the proportion with a normal model. Or, right? Or we can simplify that by saying the conditions are satisfied to perform a blank test name, and that's it, right? That's all we can. I mean, this is not a wrong way to write it in the first one, but it is definitely a lot more complex. All you really need to say is that the conditions are satisfied to perform this test, okay? And we'll name this test here in a minute. You do need to be careful, though, again, sometimes on the AP Stats test and on various, whenever you're doing like some research, it might be the case that you end the whole process here because you might have to say, because the conditions are not satisfied, I cannot proceed with the test. And if that's the case, you need to stop, reconsider your research, try to get a larger sample size, try to randomize it, do whatever you can, okay? So this one does have, every test that we do has a different name that you need to include in this report. The test that we're going to do today is called a one proportion Z test. And the assumptions and the conditions that need to be met in order to make this are a randomization condition and a sample size condition. And as it turns out, they are exactly the same as the confidence intervals that we just did, right? We need to have NP greater than 10, and we need to have NQ greater than 10. So more than 10 successes and more than 10 failures, and we're going to call that good. So let's go back to our GMV example. We have the 80% claim, but the thing showed 61 out of 90. So are these conditions satisfied? So the first thing is it random? Well, I'm going to go back to my question stem and look at that. It says 90 randomly selected local teams. So what I'm going to say down here, and again, when you're writing this as a for the AP test, you need to make sure you write a complete sentence. I'm going to write the question stem claims that teams were selected randomly. Oops, selected randomly. All right. And then our other one, the number of successes and failures, we have 90 teams being as our sample size. So 10% of 90, or I'm sorry, 80%, that's going to be our successes. I'm just doing this in my head now. 10% of 90 is 9, which means 20%, which means there's 18 fails. And if there's 18 fails out of the 90, that means that there's 72 successes. And so we need to write a sentence that says both successes and failures are greater than 10. Are greater than 10. So the sample size is large enough. And my conditions are met, which means I'm going to write conditions have been met to perform a one prop Z test. So notice that I stated both of my conditions. I wrote complete sentences that showed not only that I calculated something, but that I also understand that those calculations are both bigger than 10. And then at the end here, I said that my conditions have been met and I named the test. Part 3, mechanics. The mechanics is where we actually do the calculation. It's where we find the p-value. Different tests have different formulas and different test statistics. So we're going to have many of these that we're going to have to learn throughout the next couple months. Usually the mechanics are handled by a statistics program or a calculator, and I will show you guys how to do that, just not in this video. But it is good to know the formulas. So here's the formulas. We are trying to find the p-value. The p-value is the probability that the observed statistic value, or an even more extreme value, could occur if the null model were correct, if the null hypothesis were true. If it's small enough, we're going to reject it. That's part of our conclusion, though. The p-value is a conditional probability. It's the probability that the observed results could have happened if the null hypothesis is true. So, here's our test statistic, okay? When the conditions for a 1 proportion z test are met, we test this hypothesis by finding this test statistic. Now, you might notice that this is basically the same thing as a z-score, except instead of comparing observed to mean, we're going to compare the observed value with the hypothesized value. And then we're using the standard deviation of that observed value, which is down here. And then again, notice that this is P sub 0, Q sub 0. It is the same thing as our hypothesized value. So we find this z-score. Once we find the z-score, we plug it into our normal CDF command, and that will tell us what the p-value is. So let's take it here. What's the p-value? I got to remember. Nope, I didn't. So, a large city's Department of Motor Vehicles claim that 80% of the candidates pass driving tests, but a newspaper reports that 90 randomly selected local teams who had taken the test found only 61 passed. What's the p-value? So, the p-value is going to be, essentially I'm going to start calculating a z-score. Okay, so remember, z equals p hat minus p sub 0 all over the standard deviation or the standard error of p hat. So this is going to be p hat, which is 61 over 90. Let's actually find that that decimal though. So this is 0.67, and my observed value is the 0.8. That's what I was saying up here, right? That's our 80% observed, our hypothesized value. And then down here we have the standard deviation of 0.8 times 0.2 all over my sample size of 90. And I'm going to find that value. 0.67 minus 0.8 is negative 0.13, and that's all over the square root of 0.8 times 0.2. And I need to divide that by 90. Oops, I need to divide that by 90. I messed up my calculation. You can't tell, but I'm doing something on my calculator. There we go. Divided by 90. When I do that, I get 0.0422, and then we do this last division, negative 0.13 divided by 0.0422, and I end up with negative 3.0805. We'll go a couple things out. So that is my z-score. This is, however, not my p-value. I'm looking for all of the things that are smaller than that. Remember, the picture of what I just found was on a normal model. I found that my z-score is over here, and now I'm going to look for all of this information that this and smaller could possibly, what would that be? And so that takes us to the normal CDF command. And remember, we want to do lower comma upper. So our lower is negative 10 and our upper is negative 3.08. Remember, it's a lower bound and an upper bound. And when we do that value, it will tell us what our p-value is. Negative 3.08. And that value is 0.00103. So my p-value is quite small. Remember, this is the probability that I would see a sample of 61 out of 90, given that the 80% is true. Like, if 80% is the actual amount, the probability that I would get this sample of 61 out of 90 is about 0.1%. So that's my p-value. I will show you in the next video a calculator shortcut for doing the hypothesized value, or for doing the test. For now, let's finish up the last step, and that's writing a conclusion. So the conclusion of a hypothesis test is always a statement about the null hypothesis. What have we shown about the null hypothesis? It must state either that we reject it or that we fail to reject it. And as always, we should always make sure the conclusion is in context. In fact, it should never be the end, by the way. This is like, in terms of your research, it should never be the end of a testing procedure. This usually, once we have this information, we then use this information to take some kind of action on policies or some kind of change, right? If it's found that significantly less teens are passing than the 80% that's claimed, this might be sort of evidence that we would use that we need to increase the education for driving in our schools, right? We're getting significantly less than we should, so let's change something. To help you remember the proper way to write a conclusion, there's a nice little acronym here. Remember, we want to finish up our process, relax, reflect, and take a nice craps. Okay? So take a craps, because when we take a craps, we write a good conclusion. The C, we need to write in context. Whatever we write about, it has to be in context. The R, we need to reject or fail to reject the null hypothesis. We have to state that in there. Assume significance. We're going to talk about in chapter 21 exactly what this means. Basically, though, it's talking about what's the threshold we're using to reject or fail to reject. Again, future topic, we'll do more. But the P then is state the P value. I don't know why I drew that line. It has no reason to be there. So, those are the things that have to be a part of your conclusions. Again, just for good statistical writing and what they expect out of you on the AP test, let's write a conclusion for our DMB example. So, what can we conclude? Because the p-value is very low, right? And remember, it was less than 0.05. I reject the null hypothesis. I'm going to say the null hypothesis is not true, okay? And this is me stating my p-value. These survey data provide strong evidence that the passing rate for teenagers taking the driving test is lower than 80%. Notice that here's my context, right? And notice that we didn't say it's true, that it definitely is, but that it provides strong evidence for. We're not saying anything definitive. This is the part that definitely has to be there. The second part is a good explanation. That doesn't have to be a part of every conclusion, at least written like this. But this is really what it means. If the passing rate for teenage driving candidates were actually 80%, we'd expect to see success rates this low in only about 1 in 500 samples, or about 0.2% of our samples. This seems quite unlikely, casting doubt that the DMV's stated success rate applies to teens. All right, and that's the end of this particular video. We'll have at least one more video in this chapter showing some calculator examples, how to do the hypothesis test on a calculator, and also just several examples of problems doing hypothesis tests. That's it for now. Thanks for watching.